Can we scavenge enough power from the Scottish winter sun to run our low power electronics forever? A few videos back I tried to get my Christmas lights to work off solar power, but the results were not impressive. But I haven't given up, I'm determined to make solar power work. The problem is, the sun is weak and the days are very short. Even on a bright day, with the small solar panels that I'm using, we rarely generate enough voltage to charge a lithium cell. However, even when there is very little light, we do still get some power from the panels. What if we could harvest all that wasted power and store it in the battery? We might be able to keep a low power electronic device running indefinitely.
It's alive! It's alive! It's alive! It's alive!
I made this really nice ePaper weather display a while back. It's super energy efficient. It uses the ESP32's deep sleep mode to great effect. It only wakes up every 30 minutes to fetch a new forecast and update the display, and as soon as it's done, it goes back into deep sleep. Now an ESP32 in deep sleep mode can use as little as 10 microamps. That's pretty amazing. The ePaper display is also fantastic. Once you've displayed the image, you can turn it off and the image persists. It uses no power at all. With my current 10,000 mAh battery, my weather display lasts for 2 to 3 months before it needs to be recharged. So I've slightly modified the code for the ePaper display so it measures the battery voltage and sends it to a server. We should get a reading of the battery level every 30 minutes. I've left this running for just under a fortnight. The results are quite noisy, but we can see a trend of the battery slowly draining over time. Now it does drain very slowly, so this feels like a great system to experiment with a bit of energy harvesting. Can we scavenge enough power from the solar cell to keep its battery topped up? I've found 2 potential boards on AliExpress that seem to be perfect for the job. We've got the BQ25504 and the BQ25570. Both these devices operate in a very similar way. The main difference being the BQ25570 includes a buck-regulated output that can be used to power a load. When the device first starts up, it needs around 600 mV on the input, and it uses this to charge up the capacitor on the V-store to 1.8 volts. Once it reaches this value, it can extract power from the input voltages down to as low as 130 mV, and it can boost this up to charge the battery. Not bad at all. The BQ25504 board is the simplest, so we'll look at that first. I've wired up one of my solar panels to the input, and if we measure the voltage on the V-store output, we can see that it's charging up. Our input from the solar cell is only around 300 mV, but we're able to charge up the V-store to a much higher voltage. The voltage on the solar cell is quite low because it's under load. If we measure the open circuit voltage, it's much higher. Eventually our V-store voltage reaches 3.172 volts, and that same value is available on the VBAT output. We would normally use this to charge our battery. Unfortunately, it's a bit too low for the lithium cell that I want to use. We'd need something closer to 4.2 volts. The AliExpress listing provides a schematic for the board, so we don't need to do too much reverse engineering. I've transferred the values from their low-resolution image onto the nice clean schematic from the datasheet. We're interested in the value of the VBAT-OV pin. This sets the maximum value for the battery and storage before charging cuts off. The equation to calculate this is here. On the board, we have an ROV2 of 3.6 MΩ and an ROV1 of 5.9 MΩ. The V-bias for the BQ25504 is typically 1.25 volts. Plugging these values into the equation, we get 3.02 volts, close enough to our measured value given the various tolerances involved. Now we could change one of the resistors to a 3 MΩ resistor. That would give us a VBAT-OV of 4.125 volts, which is pretty close to the ideal 4.2 volts that we'd want. But I don't really fancy changing these tiny resistors unless I really have to. Let's see if the BQ25570 board is more suited to our needs. I spent a bit of time reverse engineering the board and created this nice schematic. It did take me quite a while. Of course, as soon as I'd finished my reverse engineering, I found a website where someone had already done it. It's full of really interesting information and goes into detail on how the IC works. Using the equations from the datasheet and the resistor values we've reverse engineered, we can see that charging will cut off at 4.07 volts and the battery OK signal will turn off if the battery voltage is less than 2.8 volts. Our board should be good for charging lithium cells, especially as my cell has protection built into it. The BQ25570 provides a buck-regulated output that you can run your load from. With the resistors on the board I have, this will output just over 2.5 volts. It's pretty nice, as you can use the output of the battery OK signal to enable and disable the buck regulator. If the battery is too low, then the output will turn off. Now you may be thinking that 2.5 volts would be way too low to run an ESP32. Isn't it a 3.3 volt device? Well, actually, the ESP32 can run on anything from 2.2 volts up to 3.6 volts. I've got one of my ESP32 dev boards connected up to the buck output running the basic blink sketch, and it works quite happily. Now unfortunately, the output of the buck regulator is limited to a maximum of 100 milliamps. That's fine when the ESP32 isn't doing very much, but as soon as you want to use Wi-Fi or Bluetooth, the current requirements shoot up. To see just how much the weather display needs when it's updating, I've placed a shunt resistor in line with the power from the USB supply. I've put three 5.6 ohm resistors in parallel, which gives us around 1.9 ohms. We can measure the voltage across this using my oscilloscope and work out how much current is flowing. I've captured a few screenshots from the print screen functionality of the scope. We can see that we're typically only measuring around 100 millivolts, which is equivalent to about 50 milliamps, well within the 100 milliamp maximum. But we have spikes of up to 600 to 800 millivolts, which is around 300 to 400 milliamps. So that won't work at all. Now we could try adding a large value low ESR capacitor to the supply to handle these current spikes, but it may not give us a very stable system. Fortunately, we don't need to use the output from the buck regulator, and if we don't enable it, it won't use any power. We can just connect our load directly to the battery, and this will easily be able to power the ESP32 with the current that it needs. So the BQ25570 board is perfect for our needs, no hacking around with the resistors required at all. I've wired it all up to the ePaper display and put it back into its usual place. It's not very pretty, but we'll build a nice box for it if it actually works. I've left it running for a week or so, and we've got some interesting results. But before I show you, it's time to talk about PCB Way. I know you're probably sick of me telling you about them, but they are really good and they've supplied me with a lot of great PCBs over the last few years. Click on the link in the description to see what they offer. So, drum roll please, the results are in. Our battery is still going down, but it is getting charged up during the day. You can see the days when we had a nice bright sunny day and the days when it was grey and miserable. But during the night our battery is going down, and unfortunately we're not able to get enough charge during the day to make up for it. However, if we do compare the slopes of the trend lines before and after adding the energy harvesting, things are slightly more promising. We can see that we've definitely had a big impact on the battery drain. We might be able to get the battery to last 1.5 to 2 times the length of time it does currently. This may be enough to get us through the long winter months when the days are short, into summer when the days are really long, and that may be enough to charge the battery back up for the overnight drain. It may even be enough to charge the battery back up so it lasts through the next winter back into the following summer. Now, there is a question that I'm sure a few of you are asking. Why are we updating the weather display at night time when everyone is asleep? If we put the weather display into deep sleep overnight, we may be able to keep the battery topped up during the day, even in winter. I've modified the code slightly so that if the time is after 11 PM, we deep sleep for 6 hours. This should save a lot of battery power, but we'll need to leave it for a while to see what happens. Fortunately, I'm off on holiday for a few weeks, so fingers crossed that everything keeps working while I'm away. On that note of everything working, I thought it would be worth actually checking it is working before I head off. So I've measured the battery voltage and I'm going to leave it on the windowsill to see if we do get some charge. The day did not start off looking good. Where the hell is the sun? But later on, things cleared up. We have some sunshine. Look at my little gadget go crazy. After a few hours of reasonable weather, we've managed to charge the battery up from 3.85 volts to 3.88 volts. That may not seem much, but if we map it onto the charge curve of a lithium cell, it's about 4 to 5%. What about the deep sleep current of the ePaper display? Is it really low power? I can monitor the current drawer as the weather is refreshed. We get a similar chart to what we saw in the oscilloscope. But once the ePaper is in deep sleep mode, we can't measure anything, it's too low. So what I've done is put a 1K shunt resistor in series with the power supply. While the display is refreshing, I'm short-circuiting this resistor with a jumper wire. Once we've gone into deep sleep, we can remove the jumper wire and measure the voltage drop. We get 167 millivolts, which is equivalent to 167 microamps. It's not the 10 to 20 microamps that we could get from a tiny Pico board, but it's pretty low. Well, I've been away for a few weeks and we've got some results. The weather in Edinburgh while I've been away has been pretty atrocious, but we have managed to get some sunny days and the days are starting to get longer. Our battery is still going down, but with the changes to our code, we're now only losing about 0.9% per day. On the sunny days, we do actually seem to be getting some charge into the battery. I'm going to monitor the situation over the next few months, but for now, I'm going to call this a success. We can salvage power, and I think our weather display may run indefinitely from now on. All I need now is a new box for it.